So to distinguish salt solutions, we must spend time identifying the cation and the anion of the salt itself. So each cation is going to belong to a strong or weak acid or base, and each anion is going to belong to a strong or weak acid or base. So if you have a salt that consists of the cation of a strong base and the anion of a strong acid, then guess what, folks? It's going to yield a neutral solution. So let's go ahead and talk about why. Well, the cation of the strong base and the anion of the strong acid actually do not react with water to produce any additional H3O plus or OH minus. So normally when we're thinking about acidity or basicity, that means we're contributing OH minus for basicity, and we are contributing, of course, H3O plus or H plus as we call it for acidity. And the cation of a strong base and the anion of a strong acid do not provide any additional amounts of that. So we're only going to be getting those amounts from water or whatever the solution is, right? So let's go ahead and get into an example. An example would be NaNO3. First, you want to identify the cation and the anion. As you can see, this breaks into Na plus, and this is going to be NO3 minus. And so this means that we have to identify and verify that Na plus is the cation of a strong base. So that means you definitely have to remember what a strong acid is and a strong base. And we know anything outside of those are going to be weak acids and weak bases. So yes, Na plus reminds me, of course, of my NaOH, Black Panther, right? Which can completely disassociate into Na plus and OH minus. Because of that, this Na plus is then going to have the ability to be in a salt solution here and be neutral in water. Why doesn't it react with water? Well, if we're thinking about metals that are charged, we said that we like to have small, highly charged metals, like say Fe3 plus or aluminum 3 plus, for example, right? Small and highly charged. Guess what? Sodium is neither small nor is it highly charged, so it definitely will not be able to react with water and cause any acidity. So therefore, it's going to be no reaction on that side. Now let's talk about our nitrate ion. We know the nitrate is going to come from the strong acid HNO3 Thor, which is going to dissociate into NO3 minus and H plus. And so that H plus is going to be our H3O plus. Well, guess what? This NO3 minus is definitely is a weak base, right? Or a weak conjugate base of this strong acid here. But it's much weaker than the base that is of water. And so because it's much weaker, it's not going to react. So if it doesn't react, that means the water is going to be the one that's going to act as a base and accept any protons, for example, which is another reason why there's no reaction here and it becomes neutral. So if I have two of these, one cation and one anion, and two of these ions here, and they both are not going to react with water, that's how I'm able to get a neutral solution. What are some other ions that do not react with water? We can have other anions like Cl minus, Br minus, and I minus, of course, because they come from strong acids, right? We also can have HNO3 and perchloric acid here. These are the anions for those. We also can have cations like our group 1 cations and our group 2 cations, which we know is going to help us understand or remember strong bases. So this is how we're able to say, okay, if I have a cation of a strong base and an anion of a strong acid, I'm dealing with a neutral solution, or I'm probably going to have a lot of spectator ions. In the lab, one of the biggest ones we focus on is NaOH. Do a different color here. We did NaOH and we did HCl a lot for our titrations, right? And so now we understand why our Na plus and our Cl minus are completely spectator and did not react with water. So now we go forward. We're going to talk about salts that yield acidic solutions. And there's two types of situations or recipes that you can bring about that's going to cause an acidic solution. The first is going to be the cation of a weak base. So if you have a weak base, its cation is basically its conjugate acid, right? And then an anion of a strong acid. So we've already seen the anions of a strong acid. That kind of helps us layer information. So we have an example here, NH4Cl minus. So as you can see, our Cl minus is not going to react with water. But our NH4 has the ability to react with water because it is the cation NH4 plus. And NH4 plus is the conjugate acid of our weak base, NH3. So once NH3 as a weak base itself is going to accept a proton because it has lone pairs, it is going to form the conjugate acid, which is NH4 plus. And because it's a conjugate acid, it has the ability to be what? Acidic. And so one way to verify that is to take our conjugate acid here, mix it with water in equilibrium to form NH3, which is our weak base, and H3O plus. That H3O plus is what contributes to acidity. One example will be like taking NH3 Ironman and of course HCl Hope and using their particular cation, so NH4 plus and Cl minus, to form the salt you see here. That's one way to get an acidic solution. let's think of another way. Another way, which is number 2, is going to be that you have a cation that is a small, highly charged metal, right? So if you have a small, highly charged metal plus the anion of a strong acid, which we know is going to have no reaction here, then guess what? You are going to have an acidic solution. So how do you get an acidic solution? It's going to be that small, highly charged metal. For example, if we have Fe H2O6 3+ Mysterio, it's the Fe3+ that's going to form the complex ion and produce H3O+ in solution, causing it to be acidic, right? Whereas the NO3- from HNO3 is going to not have any reaction in water, and it will have no reaction as we see here. And an example salt would be FeNO3-3. Of course, our Fe is going to come from our small, highly charged metal, and our nitrate ion is going to come from our strong acid, HNO3. And next, we have salts that yield basic solutions. So for a basic solution, we need the cation of a strong base. And the cation of a strong base, we know is not going to have any reaction like we saw before, right? And then we're going to need the anion of a weak acid. So the anion of a weak acid, it's going to be its conjugate base. And when you have the cation of a strong base and the anion of a weak acid come together, you're going to form a basic solution. So let's get an example salt. And of course, this salt is going to dissociate. And when it dissociates, we're going to get CH3, COO-, and of course, Na+. This Na+ or sodium plus is going to come from our NaOH Black Panther here, which is going to dissociate to Na+, and we know it's not going to have any reaction. But we do have the CH3COO- here. And this is the conjugate base of our weak acid, which is going to be acetic acid, Dr. Strange. And so I always kind of write out the conjugate acid base pair like you might have seen before. And so I'm going to take my conjugate base and mix it with water to verify that I'm actually forming a basic solution. So I have CH3COO- plus water is going to form the weak acid here, acetic acid, plus OH-, confirming that yes, it does create a basic solution. So of course, we got to get into an example. We're back at the Avengers compound, right? We got to go ahead and gather any expressions or relationships or understandings, assumptions that we can use to help us answer this question and get to it. So it says, predict whether aqueous solutions of the following are acidic, basic, or neutral, and write an equation for the reaction of any ion with water. So again, we have to use our understanding of salt solutions that can produce neutral, acidic, or basic based on our understanding from the previous portion of the video. And then we're going to write an equation, which essentially just means take whatever weak acid, weak base that you have and mix it with water, right? If it does provide any kind of acidity or basicity. If it's neutral, we ain't got to do all that. So the first thing I want to do is basically go out and kind of get all of my different cations and anions. So I have KClO4. That means I'm going to have K+ here, and I'm going to have ClO4-. Here I'm going to have C6H5, COO- and Na+. Here I'm going to have Cr3+ and NO3-. And then here I'm going to have C5H5, okay, NH, and then I'm going to have Cl-. Okay, I have all of my cations and anions, and then of course we have to use the relationships before. So if you have flashcards, this is going to be that time to kind of use that for your advantage in the memorization portion. And after I get all my cations and anions, the next thing I do is get rid of anything I know doesn't have a reaction because they're coming from strong acids and strong bases. Because I've had my strong acids and strong bases memorized, I know that K+ is coming from KOH, I can get rid of that. Na+ is coming from NaOH. NO3- is coming from HNO3, and CO- is coming from HCl, okay? So because of that, now I only have these particular ions to focus on. Oh, I also see ClO4-, which also is coming from a strong acid, okay? So because of that, I got rid of both of these ions here, so that means this definitely is a neutral solution. That one's pretty nice, right? Let's go to the next one. I only have C6H5COO- left, and you have to ask yourself, what is this? Is it a weak base? Is it a weak acid? Is the conjugate acid a base of something else? What does it come from? So I'm going to specifically just call out letters B, C, and D with all of their respective ions. So I have an anion here and 2 cations. And I have to ask myself, is this the anion of a weak acid or base or a strong acid or base? Now, we've already got rid of anything that could be related to a strong acid or base, right? So we know we're dealing with weak acids and bases here. What I do is I'm either going to accept a proton or donate one in order to be able to show that conjugate acid-base pair. So this has to be the anion of a weak base Why? Because when I rewrite this and I go ahead and accept a proton, for example, I get C6H5COOH. And this is definitely going to represent the anion of a weak acid. And I totally wrote base, apologies. Once I definitely accept a proton, then I am creating a weak acid, right? So this is actually the anion of a weak acid. How do I do that? I just go ahead and accept a proton to form C6H5COOH. And then when I remove the proton, I get the C6H5COO minus. And so because it is the anion of a weak acid, that means this is its conjugate base. And the conjugate base is going to make this one basic, folks. So let's go ahead and do that for the rest. You basically want to try to come up with a I would say conjugate acid-base pair. If you can't, you need to go further and outside of conjugate acid-base pairs, think of complex ions that can be formed, et cetera, et cetera. So let's go ahead to letter C here. And as I can see in letter C is Cr3+. I see this as a metal, so it is a cation. Not the cation of a weak base or acid, it's the cation of a small, highly charged, because it is 3+, metal. And because that's true for Cr3+, then we will say that this is automatically going to be acidic. Okay, because any charged metal has the ability to form a complex ion and then produce H3O+ in solution. So I will say this is acidic, and I'll write it here and here. And then finally for letter D, we have C5H5NH+. As you can see, there's already a proton attached. So what I want to do is say, okay, this has already accepted a proton, so I want to release the proton here and see what I get. I'm going to get C5H5N. And so as you can see, once you accept the proton, you get the H+, and so this must be a weak base. So that means the cation of it is going to be its conjugate acid here. And so this is the cation of a weak base. How do I verify that? I took away the proton, and then I pretended again like I was creating a whole new conjugate acid-base pair. So I'm like, if I have it here as C5H5N, and then I go ahead and accept a proton, then I'm going to have a C5H5NH+. Therefore, I'm going from a base to its conjugate acid if I'm thinking of conjugate acid-base pairs. So this one is therefore going to be acidic, okay? And that's how I would approach this question, just by simply using what we have saw before. Again, you can go ahead and start creating a flashcard. I would recommend just getting one single flashcard and then breaking it up into 3 parts, neutral, acidic, and basic, and going ahead and getting examples for that. But the real work of these type of problems is being able to know what strong acids and bases are, and therefore know that everything else has to be a weak acid and base. And then, of course, knowing little details about like the highly acidic small charged metals or the non-metal hydrides, things like that. And of course, the different patterns of electronegativity, bond length, and bond strength as well.